Have you ever been absolutely sure about something, only to get one new piece of information that changes, well, everything? Of course you have. We all have. Well, it turns out there's a mathematical rule that actually governs that whole process. It's called conditional probability, and it's basically the engine that drives learning. It explains how our view of the world should shift when we find out something new.
Okay, so to get our heads around this, let's start with a classic puzzle that trips up pretty much everyone. It's the Monty Hall problem. So imagine this. You're on a game show. 3 doors. Behind one is a brand new car, behind the other 2, goats. You pick a door. Then the host, who knows where the car is, opens one of the other doors, shows you a goat, and asks, do you want to stick with your original choice or do you want to switch? What do?
All right, let's say you pick door number 1. Right now, at this exact moment, your odds are pretty straightforward, right? You have a 1 in 3 chance of having picked the car, which of course means there's a 2 in 3 chance that the car is behind one of the other 2 doors. So far, so good. But now, here comes the twist. The host opens door number 3, and there's a goat. Now, this is the crucial part. This wasn't a random act. He knew where the car was, and he deliberately showed you a goat. So now you've got this new critical piece of information, and the choice is yours. Stick with your original pick, door 1, or switch to door 2. Now your gut, my gut, pretty much everyone's gut screams that it's 50-50 now. I mean, there are 2 doors left, 1 car, what else could it be? But the math is just shocking. You should absolutely 100% always switch. Switching your choice literally doubles your chance of winning to 2/3. So the real question is, what on earth is going on here? Why?
This puzzle is just a brilliant example of how our brains are not naturally wired for this kind of probabilistic thinking. We tend to just hit a reset button and see the final choice as a simple coin flip, totally ignoring the history of how we got there. The key, the whole secret, is understanding how that new piece of information, the host opening a specific door, completely rewrites the probability landscape.
To really get why, we need to look at the fundamental tool for this kind of reasoning. So let's talk about shrinking the world of possibilities using something called conditional probability. Okay, so formally, you'll see it written like this: P of A bar B. That vertical bar just means given. So it's the probability of A happening, given that B has already happened. It's just a structured way of asking, okay, based on what I just learned, what are the chances now? And I love this way of thinking about it. Every new piece of information you get literally shrinks the universe of what's possible. You're not dealing with every single outcome that could have happened anymore. Nope. You're now living in a new, smaller universe, populated only by the outcomes that are still on the table. And this shrinking act changes everything. Let's make this super concrete. Say you roll 2 dice. You have 36 possible outcomes, right? 6 sides on the first die, 6 on the second. The chance of rolling, say, a sum of 5 is 4 out of those 36 possibilities. But what if I give you some new info? What if I tell you that neither die landed on a 1 or a 6? All of a sudden, bam, our universe of 36 outcomes shrinks to just these 16. Now, let's look for a sum of 5 inside this new, smaller world. The only ways to do it are a 2 and a 3, or a 3 and a 2. That's 2 outcomes out of 16. The probability shot way up. The new condition changed the whole game. This whole idea of updating our odds as we learn more has a name, and it gives us a really powerful framework for thinking. It's time to talk about updating our beliefs. So if conditional probability is like taking a single photograph, a snapshot in time, then Bayes' theorem is like filming the entire movie. It's not just about a one-off calculation. It's a formal system for continuously learning and revising what we believe as new data rolls in. And it works in 3 beautifully simple steps. First, you start with a prior belief. That's just your initial guess. Then you get some new evidence, which we call the likelihood. Finally, you combine those 2 to arrive at a new, updated posterior belief, which is, hopefully, a little closer to the truth than where you started. But here's its real superpower. It lets us work backwards. See, it's often easy to know the probability of an effect given a cause. Like, what's the chance a smoke alarm goes off if there's a fire? But Bayes' theorem lets us flip that right on its head. It helps us find the probability of the cause given the effect. So what's the chance there's a real fire given that the alarm is blaring? That's a much more useful question. Let's see this in action, because this trips people up all the time, even doctors. Imagine a disease that affects about 9% of people. There's a test for it that's pretty good, but it's not perfect. Now, if 1,000 people take this test,
This is how the numbers would roughly break down. And just notice something really interesting. The number of true positives and false positives is exactly the same. So, you get a positive test result, your heart sinks. What are your actual chances of being sick? It's a coin flip. 50%. How can that be? Well, think about it. A total of 164 people tested positive, but only half of them, the 82 true positives, actually have the disease. This is a classic trap called the base rate fallacy. We get so focused on the shiny new test result that we completely forget how rare the disease was to begin with. All right, now that we're armed with these new mental tools, we can finally go back and make sense of those bewildering puzzles from the beginning. So let's finally crack the Monty Hall problem. Remember, your first pick had a 1 in 3 chance. That means the other 2 doors combined started with a 2 in 3 chance of hiding the car. Now, when the host opens one of those doors to show you a goat, he's not doing it randomly. He's giving you priceless information. He didn't change that initial 2/3 probability, he just concentrated all of it onto the one door he didn't open. So when you switch, you're not just picking another door at random, you are claiming that entire original 2/3 probability all for yourself. The Monty Hall problem shows how hidden information can totally fool our intuition, but sometimes it's the way we group our data that's just as misleading. And this leads us to another famous statistical illusion, Simpson's paradox, where a trend you see in small groups can completely disappear or even reverse when you combine them. This is a classic real-world example. Back in 1973, UC Berkeley's overall admission numbers looked like there was a clear bias against women. But when researchers started conditioning the data, when they looked at it department by department, the trend flipped on its head. Women actually had higher admission rates in most of the individual departments. So what was happening? The paradox was caused by a hidden variable. Women were, on average, applying to much more competitive departments, which had lower admission rates for everybody, men and women. So after all these mind-bending examples, what's the big takeaway here? How do we actually use this to avoid these kinds of traps in our own thinking? You know, if there's one single thing to take away from all this, it's this. Probability isn't some fixed, static property of the universe. It's a dynamic reflection of our knowledge. And as our knowledge changes, our assessment of the probabilities must change right along with it. That right there is the very essence of learning. And to start thinking this way, you just have to train yourself to ask a few key questions anytime you get new information. First, what exactly is the new piece of info? Second, what was my starting point? What was the base rate? Third, how does this new fact shrink the universe of possibilities? And finally, based on all that, how should I update my belief? So I'll leave you with this question to chew on, because once you start seeing the world through this lens, you realize something pretty profound. A lot of our strongest convictions are really just probabilities, patiently waiting for the right piece of evidence to come along and change them completely. And being open to that change, well, that's the first step toward really understanding anything.